Welcome back. Right. So we're going to start this section off with an example. We want to compute the double integral of 3xy over this region D, which is bounded by these four lines. Right. So as I've been saying over and over, the first thing you should do is sketch the region. Right. So let's sketch this. All right. So, well, these are diagonal lines going this way. So, and they pass through 0, 1 and 1, 0. Right, so we get something more or less like this here. So say this is 1, this is 1, then this guy, x plus y equals 1, is this line. Right? Okay. Then, if we go to the next line, which is parallel to it, x plus y equals 4, we're going to have the same thing, just moved up to 4. 1, 2, 3, 4. Right. So we get this parallel line. Okay. And this is x plus y equals 4 down here. All right. And now we got to graph the other two lines. Well, we have x minus 2y equals 0. So that starts here. And then if x is 2, y is 1. So we get a line like this. Right, so this is x minus 2y equals 0. And then x minus 2y equals negative 4 is parallel to that. So if x is 0 there, y should be 2. Right? And then we can just make it parallel, or we can do if x is 2, then y should be 3. Right, so we get somewhere, x is 2, y is 3, up here. Okay. All right, so what is this region? Well, it's this guy in here, the sort of diamond-shaped thing in here. Right? So if we were to set up a double integral, well, if we did dy first, notice that we have, oops, let's do it from the bottom. We'd have to split it into 3 regions. And if we did, dx first, we'd again have to split it into 3 regions. So we could do this, but it's going to take a while. So notice, though, that these lines here have something in common. These are parallel, and these are parallel. Right? And we can do kind of a trick here. If we say let u be x minus 2y and v be x plus y, well, what good is that going to do us? Well, that's going to change this line to be u equals minus 4. This one's going to become u equals 0. This one will be v equals 4. And this one will be v equals 1. So if we imagine graphing this in the uv plane, so here this was xy plane. Right? If we graph this in the kind of new uv plane, then we get something a lot simpler. And I'll draw the picture a bit smaller here. So u needs to go from minus 4 to 0, v from 1 to 4. So let's set up our axes here. Right, let's say this is u and v. So v needs to go, here's 4 and 1, and u needs to go from minus 4 to 0. Right. So what does the region look like here? Well, these are the two u lines, u equals -4, and then u equals 0 will just be the v-axis, right? And then v equals 1, and v equals 4. Right, so v equals 4, v equals 1. Let's go ahead and label these two. U equals -4, u equals 0. So if we do kind of a change of coordinates like that, we get something nice. And this is kind of like the idea behind polar coordinates and behind cylindrical coordinates and behind spherical coordinates. We're coming up with a new coordinate system that allows us to express whatever we're trying to integrate over in a much nicer way, right? But it still comes down to, how do we integrate this, right? So if this region here is D, maybe we'll call this R, right? How do we go from D to R? Well, we have this system of equations here, and we can solve it for x and y, right? So we can take this guy, solve for x and y. So for example here, if we take u plus v, if we do u minus v, or v minus u even, so v minus u, that'll give us x minus x, and then y minus 2y, so 3y, right? And then that'll tell us y is v minus u over 3. All right, that's great. Okay, now if we do, what do we need to do this time? We need to take 2v and add u, right? That'll give us 2x plus x, so 3x, and then 2y plus -2y, so 0. Right? So x will be 2v plus u over 3. So we can even solve for x and y. And then, well, that allows us to take the x and y here and plug it in up there. But now, the fun guy. Just like with polar coordinates, just like with cylindrical, just like with spherical, we have to change that dA. Well, in cylindrical and spherical, it would be dV, but thinking back to polar, we have to change this dA. Now, what does that dA become here, though? And that's the question. That's the tricky question here. Well, what it's given by, dA, will be given by something called the Jacobian, the absolute value of the Jacobian, and then we'll have du dv, right? And we denote the Jacobian by, we always here want to take sort of derivatives of the old variables with respect to the new ones. So it looks like dxy minus, or over du comma v, right? So what is that kind of saying here? It's kind of saying take the derivative of x here with respect to u and v, and then of y with respect to u and v. So what is this guy here? Right, so first let's box this guy off. This is the very important formula here. What is this given by? Well, d of xy, d of uv, this is going to be a determinant of something, right? So this is the determinant of a certain matrix, right? And this is a matrix of first partial derivatives of a transformation, right? But what it looks like here is we have dx du, dx dv, dy du, dy dv, right? So the notation here kind of means take the derivatives of this first thing, x, with respect to u and v. Okay, then go to the next row, take the derivative of y with respect to u and v. Right? So that's kind of where this notation is coming from. Right? So if you like, this is xu, yv minus xv, yu. I'd hesitate memorizing this as a formula here because, you know, we're going to be using different variables, not necessarily just u and v, but this is essentially what it comes down to. All right? And then when we switch dA, we take the absolute, or switch dA to du and dv, we take the absolute value of this guy and pop it in front there. So now we can set up the integral. Okay? So we're trying to do the double integral over d of 3xy dA. Okay? So the first thing we should do is compute this Jacobian. So I'm actually going to just erase the thing I just wrote, and we'll compute the Jacobian first. So d of xy, d of uv, well, it's the determinant of some 2 by 2 matrix. Right? So we need dx du. So here we have our x and y. So we have 1/3 with respect to v is 2/3, negative 1/3 and 1/3. So here we get the determinant of this is 1/9 minus negative 2/3. 2/9, sorry. So the Jacobian's 1/3. Okay? So double integral over d of 3xy dA. So double integral. Now for x we plug in 2v plus u over 3 times y is v minus u over 3. And then absolute value of this guy, that's just 1/3. And then we get to decide du or dv. Well, nothing here is particularly bad. This is a nice rectangle, so let's just say du dv. Right? So u goes from negative 4 to 0. Right? V goes from 1 to 4. Right? So it's always important here that after you've decided on your change of variables, that you take the old region and sketch it into the new region, or change it to the new one. Right? So here, let's just maybe simplify this a little bit. So this will be, that cancels with that, so 1/9 of 2v squared minus uv minus u squared du dv. And you can compute this integral and get 164 over 9. Right? At this point, doing the actual integral isn't so interesting, but changing the variables like this is. Right? So hopefully this motivational example here kind of made sense, what we were trying to do. And this should remind you actually a little bit of u substitution from Calc 1. Except you might notice the interesting thing here is we didn't do it to help us integrate this function. We did it to help us integrate over the region, which was this kind of skewed diamond that would require multiple pieces. And we changed it to a nice new region. Okay, so that's one of the ways this is going to work. Right? Okay, see you in the next video.